Recording in progress.
Okay, as the recording is in progress, I guess we have the official starting time reached. With this, I welcome everybody to this afternoon session of Seminar 2 on the first day of Laser Physics 23. There are still not too many participants in this session, but probably because the Asian participants cannot make it anymore because of time shift. We have two presentations concerning generation of radiation and one of relativistic acceleration of electrons. And we start out with the presentation by Margarita Kochlova from Max Born Institute and King's College of London, where she tells us something about boosting XUV intensities due to propagation effects. Please take it away.
Thank you for the introduction. Hello, everyone. First of all, I would like to thank the organizers for this nice opportunity to share our work, which has been done in collaboration with Vasily Strelkov, and it's quite a long-lasting project. So this work addresses one of the oldest questions of attosecond physics, namely how to advance attosecond pulses. Here we study the limitations of common tabletop workhorse for the second pulse production. And I'm talking about good old high harmonic generation process. Also, we will focus on high order frequency mixing, which is not as common as high harmonic generation is, and try to analyze if there are any advantages of generating pulses with high order frequency mixing instead of good old high harmonic generation. And let me first elaborate on our motivation. So far, the improvement of attosecond pulses generated traditionally through the process of high harmonic generation chases the following main goals. It's either making attosecond pulses shorter and thereby increasing the resolution, which can temporal resolution, which can be used to study new physical ultra-fast processes, or increasing the brightness of the attosecond pulses and thereby making them more applicable, widely applicable, or also the applicability can be widened if you come up with some additional handles for these attopulses. Here in this talk, I will mostly concentrate on boosting intensity of attosecond pulses. And here the progress follows a few different routes to squeeze as much as possible from high harmonic generation process using either propagation effects or gaining from the playing with a microscopic response, maybe even combining those two things together, or even switching to from the tabletop sources to large free electron laser facilities. So this interest to obtaining bright attosecond pulses or bright XUV pulses, I can illustrate showing this very curious publication argument in a seek of exponential amplification in high harmonic generation. And this search wasn't successful in the end. However, this argument kind of spotted the blank bit in theory that so far there was no any solid theoretical framework for the processes of this kind. What exactly I mean here, that there was a single high-order process, high harmonic generation, which was well theoretically described and understood. However, other its high-order cousins haven't been touched much. And the first attempt to theoretically explain high-order frequency mixing, high-order parametric amplification, high-order simulated scattering processes have been, this attempt has been done by Vasily Strelkov, where he explained these processes using the induced susceptibilities of the medium and nonlinear polarization of the medium when the strong laser pulse, strong laser field is many photons of this field, combined with an additional weak field where just a few photons of this field involved in this process. So this theory gives rather bulky but fairly valid answers to understand, to describe these processes. However, by then, neither of high-order processes, any theory was taken into account the ionization of the generating medium by the strong laser pulse. So exactly that's what my talk is going to be about. And I will start with well-known high harmonic, the most familiar high harmonic generation process. And we will be looking at the solution of reduced propagation equation for the electric field and taking the medium as with nonlinear polarization of it in frequency domain, where the ionization of the medium is taken into account within the time-dependent refractive index of the medium, which changes linearly around the peak of the pulse. For this problem, we can find integral but still analytical solution for the field for the spectrum of harmonics, their dependence with propagation distance, where, as you can see, the ionization is taken into account by delta n, and this is the microscopic response. And if we assume that this response has a Gaussian line shape, then this integral can be taken fully analytically in this rather compact or maybe that much form. But this is just a line shape, but most importantly, this result has a new very important parameter. Let me convince you why. Let's study this parameter more. This parameter is called blue shift length. So let's consider a few different regimes for the generation of HEG. So red lines here present the refractive index when the atomic dispersion dominates or geometric dispersion dominates. In these regimes, the propagation of the harmonic field, the energy of the harmonic with distance, its quadratic growth is limited by the coherence length, as sounds quite familiar. So the other regime is when electronic dispersion dominates, or more better version basically of this regime, it's when this atomic dispersion is compensated or transiently compensated by the electronic dispersion. Those two regimes are shown here with those two dependencies of of the harmonic energy with distance, and you can see that they both first grow quadratically, and then the quadratic growth switches to the slow one after the harmonic passes the length, which is blue shift length. So let's look at this at this propagation. Let's try to understand where it comes from. So the blue shift of the fundamental translates into much larger frequency blue shift of harmonics themselves, and this shift grows with propagation. And at some point, the fields of harmonics stop adding up coherently, which in the end just results in the broadening of the harmonic line and the energy of the harmonic growing linearly, which shows the incoherence of the process. So let's look again from a little bit different angle here. There are three different lines. One of them corresponds to the regime when the coherence length is the shortest, it is shorter than the blue shift length, and that is why it limits the quadratic growth of the energy of the harmonic, and then the energy starts oscillating, and then two other curves correspond to the regime when the blue shift length is shorter than the coherence length, and in this regime, blue shift length limits or spots the change from the quadratic growth to the linear growth. We used numerical calculations of the propagation equation coupled to time-dependent Schrödinger equation to calculate the propagation of this the field with these parameters of the argon gas, and those three regimes correspond to these intensities of the generating initially incident laser pulse, and these curves for this specific case look this way, and you can see that those numerical results quite nicely agree with our analytical theory. We can also look how changes the spectrum of the harmonic with propagation distance for the regime when the limiting mechanism is phase matching. The harmonic grows, and then it starts slowing down or even the intensity decreases, while the blue shift is not that obvious here. For high intensity, there is a more pronounced blue shift, and harmonic keeps shifting and broadening while growing still quite fast. And then you have even larger, even more pronounced blue shift, and quite strong widening, and the whole energy becomes smeared over quite a wide range of frequencies, and it's even stronger effect for higher order harmonics. So to summarize, these results for the generation, for GG generation coming from this pulse in argon, you can come up with three different mechanisms or three different regimes with three different mechanisms limiting the quadratic growth of harmonics for different spectral ranges and different intensities. For low the harmonics, the limiting mechanism for propagation is absorption. Then for low intensities, it is phase matching, and as soon as the intensities become higher, the ionization contributes quite strongly, and blue shift becomes the the dominant mechanism which limits the quadratic growth with propagation for high harmonics. So does it mean that there is no chance to generate strong XUV harmonics or pulses with tabletop sources? The answer is no. We just need to add another weak low frequency field and to consider how the frequency mixing process. In this case, when the whole field is combined of many photons of the strong field and very few photons of low frequency field, the mismatch condition can be written in this way. And for high harmonics, there is a very simple condition for strong and weak field frequencies, for which the high frequency mixing component will be always phase matched for any intensities or for any degree of ionization. Let's look if this nice model makes any sense. So we again came to our favorite tool here. It is a combined solution of time-dependent Schrödinger equation with propagation. And here you can see the generating field, strong component which experiences with propagation quite visible blue shift, and weak low frequency field which has much more pronounced blue shift and quite strong rolling. So these fields generate high harmonics and high frequency mixing components. And what happens to the high harmonic line is nicely represents our analytical results. While high frequency mixing component keeps growing quite nicely quadratically without changing its shape much, which manifests quite nice phase matching conditions. So we can look at this result from a little bit different angle. So that spectrum of the nicely growing HFM component and widening and splitting high harmonic. We carried out the calculation for another generating field where you can see the same result appearing, that harmonic, 19th harmonic here, doesn't grow any strong way as we would desire. However, these high order frequency mixing components of coming from different processes are clearly much stronger. Let's look at a couple of slices with propagation here. And you can see this is ordinary high harmonic, and all the frequency mixing processes are clearly stronger. And this is the summary of all these calculations. So the harmonic energy grows quadratically up to the point when it reaches blue shift length. When it starts slowing down for different parameters of the generating field and different components of different fields, while for HFM components this is not the case, and phase matching is not destructed, and harmonic those components grow quite well. So a little bit from the reality. This is experimental results for high order parametric generation. Here there was a generation in the capillary from the experiments carried out in Celia. The intensity grows from here to here. And for the lowest intensity of the generating field, you can see harmonics looking quite usually. Then for increased intensity, harmonics start experiencing blue shift and widening. While for even high intensity, we can see additional component here, which is this either parametric generation component, which is a mixed frequency component, which becomes stronger, even stronger, and nicely phase matched for even higher intensity of the generating field. This is the other angle at these results. I will probably comment just on my favorite one here. This is the spectral width of usual harmonics, and this is very nicely phase matched. Shifted satellites coming from parametric generation, which is fully supported by our theoretical results. So is that it, or can we study something else about high frequency mixing? So we decided that just numerical results is not enough, and we tried to understand something more, starting from a single particle response within SFA for high order frequency mixing, where we looked at two fields, very different intensities and quiet tone pulses. So first, analytically, the ratio between HFM components to high order generation components can be presented in this nice analytical ways, where we can see that the field ratio, the involvement of the field is quite clearly coming from the order of the low frequency field, like photon order of the low field field involved, which you can see here for the absolute value of these processes, and also you can see that there is a change in corresponding to HIG. There is a shift in half pi, and for one order low frequency field process, and whole pi for these kind of processes appearing within the SFA. We decided to run TDC calculations to see how reasonably this result corresponds to numerical calculations, and you can see some reasonable comparison between those two results. What else can be taken from this? So from these numerical calculations, we looked at the cutoff region, and we calculated the emission time for this zero means high harmonic generation, and those HFM components for either one photon involved or two photons of the weak field involved. And you can see that the emission time for those components where two photons involved is pretty much the same or around within this cutoff group, which results in the shortest at the second pulse you can generate using these components. Also, we found out that if we look not just at the envelope but at the field of the harmonic, the shape of the field can be controlled by the relative phase between strong field component and weak field component, and that the CEP between consecutive at the second pulses within the second within the train change by the number which depends on the frequencies of the strong and low fields involved and the order of the process we are looking at. So this result combined with any gating technique can basically mean that we can choose the generation of attosecond pulses with some given CAP. And now work in progress. We are trying to validate this result within the numerical propagation of the TDs. And to summarize, we have introduced a new length scale for high order processes, which limits high order harmonic generation, which is called bullshit length, for higher intensities of the driver. And we also offer another process, high order process, which is frequency mixing, which will help to overcome these limits which are imposed by the ionization on HEG. That has been observed for another parametric, higher parametric generation process, and this nice result with the change of CAP. We want to calculate soonish, I hope, will be published for the full propagation calculations. Thank you for your attention.
Thank you, Margarita, for your nice presentation. I see clapping in the audience. Let me start with the discussion with one short question. You had 3 bordering problems for the ordinary high harmonic generation, which also included absorption. Absorption is also included in your frequency mixing calculations. So there, since you're going to very high frequencies, absorption is not a problem there anymore. Or is there anything else that I overlooked?
Well, absorption it affects just low order harmonics.
Yes.
And they're not so interesting for us if we want to get into the XUV.
But you showed something like the 6 harmonic around this, and there you had this quadratic increase in intensity, so that's not very high harmonic.
No, it's not very high harmonic, but the frequency of the driver there for these calculations is 330 nanometers.
Oh, okay.
So in the end, it's still quite high frequency of the harmonic.
Okay, yeah. Thank you. Are there any questions from the audience? Yes, Alexander Silayev has a question, please.
Hello, everybody. I have a question. Do you propose a new regime of generation of high order harmonics, or explain some earlier experimental results?
I would say we explain overlooked pieces of theory, kind of at analysis of why it was not possible to propagate harmonics for longer distances to get strong enough, stronger intensity in the end. We analyze it, we show where exactly until when it makes sense to propagate harmonics to have some gain from the propagation. But of course, it was observed that it wasn't just probably explained in the very solid and full framework, I would say.
Mm-hmm. Okay, thank you.
I do not see any further questions, neither in the chat nor in the audience.
Thank you for questions.
So let's thank the speaker again, and thank you for answering the questions. And we now switch to the second presentation of Petrovlat Toma. Can you try sharing? Is that working well? Perfect.
Can you hear me? Can
Yes.
you hear me well?
We
Okay.
can see Ocular.
Yes.
Yeah, now then I guess the presentation will also work. So we start with the presentation of Petrovlad Toma from the University of Bucharest. And he will talk about relativistic acceleration of electrons and how they interact with a Laguerre-Gauss laser pulse. Please, thank you.
And thank you for the introduction, and thank you for the opportunity to present our group's work. I'm also working at the National Institute for Laser, Plasma and Radiation Physics near Bucharest in Magurele. So here's a bit of a plan for my presentation, a bit of theory, and then the results. First of all, the Laguerre-Gauss modes were known previous to the seminal article by Allen, where he showed that the density of angular momentum divided by the density of the energy is equal to an integer divided by the angular frequency of the pulse. And that's part of the idea that perhaps this is a way to express the orbital angular momentum of light. And that sparked a lot of interest in the Laguerre-Gauss modes. How do you obtain this field? Well, if you solve the paraxial Helmholtz equation, you will obtain this function UPM, which is written here in terms of the hypergeometric confluent function, which is in fact proportional to the Laguerre associated functions up to a multiplicative constant. And then if the propagation direction is Z, we have the freedom to assign to two directions this solution. The third will come from the divergence, and then we can also generate the magnetic field starting from the electric field. Because we're interested in the outcome of the interaction of our field with charged particles, we also need to put a temporal profile, an envelope, a temporal envelope, such that we will also have at the end final state to compare to our initial state. In particular, we've been mostly using Gaussian wings with the flat top in the middle, though a lot of the following results will be without the flat part, just the Gaussian. And I should also mention that the zeta x and zeta y can give something akin to a polarization, because we can give a field either in a plane or through complex coefficients, give something akin to a circular polarization. So this video shows what's the energy density of such a beam looks like in the focal plane. On the left, we have the linear polarization, while on the right, we have the circular polarization. And what's interesting here is that if you average over time, the linear polarization becomes the circular polarization. These rings will be a recurring feature. And they also play a role in the ponderomotive approximation, which we use later to describe or rather to approximate the dynamics we find. So for the first part, we simply simulate the manifest covariant dynamics by integrating the 4 and 4 sets of, so there's 2 sets of 4 differential equations each. And we numerically integrate these equations using differential equations JL package available in the Julia programming language. And this will present the basis for our results, as well as this part of the Faraday tensor, which includes the electrodynamic component, which we compute using a package we have written ourselves. So how this study works is that we have distributed particles in a disk of a radius R0 around the axis of our beam. And we have looked at the interactions from a statistical point of view. This means that the electrons are not interacting with each other. Rather, it's like running the experiment over and over and over to try and see if there are any interesting or meaningful features to discover. So in this video, I hope you can see it. It's a bit small. We have for different A0, we have different widths of the beam and different times of interactions. And while the reduced parameter A0 is small, we observe that the radial component dominates. And as the A0 increases, the azimuthal, the propagation direction increases. I think maybe I should have made this bigger. So when the intensity increases, the net momentum transfer is longitudinal. Moving on to angular momentum, let me explain a bit what these plots represent. Since we have worked with distribution of particles in a disk, one way to look at the result of the interaction is to scatter the points in the plane according to their initial coordinates, and then color each point according to the final angular momentum received by each particle. Interestingly, what we notice is that these regions are well defined for small A0, but also for large A0. Especially what's happening is that since the shape or the pattern of the distributed angular momentum is the same, this gave us the idea that maybe there is a scaling happening in this system. And indeed, when we look at the maximum and also at the average angular momentum transferred from the poles to the particles to our statistical ensemble, we notice that there is a region for small A0 and a region for large A0. The small A0 region is linear, while the large A0 depends on whether we have linear polarized fields, linear polarized Laguerre-Gauss modes, in which case the scaling is by a power of 2. While if we have circular polarized field, the scaling is by a factor of 4. So this difference has been strange to us, and we've been thinking that perhaps this is caused by the fact that we distributed the points evenly, and since at the beginning of the interaction, our particles have no angular momentums as they are at rest, this somehow hides a bit of the structure of the interaction. So we have this defined for us to measure the translated angular momentum, which is basically looking at the momentum of each particle in its own initial reference frame, which has actually yielded identical results between linearly polarized and circularly polarized scaling, both with a power of 4. We have also looked with this occasion at the radial scaling, the scaling of the maximum radial linear momentum, which is by a power of 2. So if we look at the time evolution of our angular momentum of the classical particles, we can see that as the pulse reaches the focal plane where our particles are waiting for the pulse, each individual particle, but also the maximum angular momentum increases. And then it also decreases as the pulse goes beyond the point where our particles were. And they leave the distribution in a fixed pattern. What we can also observe here is that by the end of the distribution, sorry, can I stop? Okay. By the end of the interaction, the linear polarized case presents this circle, or rather annulus components, which match geometrically speaking, but have opposite signs, which indicates that there is no net angular transfer. Meanwhile, for the circularly polarized case, the final distribution will take the shape of a number of concentric rings of the same sign. And this suggests to us that there is net angular momentum transfer to our ensemble. This can be more clearly seen when we are looking at the laboratory-based translated frame histograms of where the x-axis represents the z-direction angular momentum and the translated angular momentum respectively, where for linear polarization the distributions are centered in 0, while for the circular polarization, as A0 increases and approaches a relativistic regime, where A0 is at least 1 or beyond, the distribution clearly skews to the left, indicating a net angular momentum transfer. Somehow, from this, we can draw the conclusion that the orbital angular momentum number m, or azimuthal index, if you like, is less important than the polarization of the light. Given that we've previously seen that the oscillations are problematic, but at the end cancel out, we have decided to also attempt to use the ponderomotive force approximation, whereby we consider the case of a particle in the presence of a field which has 2 time scales, and we average out the fast oscillations and remain with a simpler problem with only the long time scale. In our case, we integrate over the oscillations of the electromagnetic field over T. And this produces what is called the dressed mass, which is dressed mass of a particle in the presence of the vector potential A, which will subsume all of the dynamics of our particles. We also have new equations of motion, which we can also integrate just like we have before. How we can integrate this ponderomotive equation of motion is that this new force-like object, momentum-like object, the change in this momentum-like object is given by the gradient of the dressed mass. For our fields, for the fields we have simulated, the dressed mass looks like this. We see again the rings, and basically wherever the color is 1, nothing interesting is going to happen from a dynamics point of view. It's basically the field is not there. So if we compare for this case, the agreement is very good, even passing the relativistic threshold of small a0 equal 1. And what we see is that as the gradient of the field moves, the oscillations add and take and add and take, yielding a similar result as our averaged potential, if you like. So we can see from this graph that there is an effect of repulsion, let's say, sending the particles away on the transverse plane, and there is a longitudinal displacement, which is in good agreement between the exact equations presented from the equations of motion at the start and these new ponderomotive equations. Similarly, in the case of the velocity, the agreement is very good. And we can also see that this velocity on the z direction increases and then decreases, which is consistent with the displacement in that direction. One way to validate this agreement is that if we look at the histograms, on the left we have the linear momentum, and on the right we have on the left we have the linear momentum in units relative to the maximum linear momentum for a given A0. And on the right, we have the difference between the exact and ponderomotive approximation linear momentum calculated. And we see that for about every A0, we have a difference in about 4 orders of magnitude between the difference and the linear momentum. We have considered maybe doing a relative error, but that is problematic because given our statistical ensemble, there is a possibility of either numerical error or a rogue particle causing huge relative error, but there being very few of them. So I think this visualization is easier to understand. So moving on to conclusions. We can see that at low intensity, the acceleration is radial, and when the intensity increases, the net momentum transfer is longitudinal. There's also important effects from the width of, the waist of our beam, which as the waist decreases, the longitudinal momentum increases, and with the time of interaction, and as time increases, so does our longitudinal momentum. There's also clear scaling properties of both the angular momentum, translated angular momentum, and the linear momentum. And the fact that we have obtained those very good regions, very well-defined regions in the scatter plots is an indication that the dynamics are not chaotic, and can possibly even we could even possibly find approximations, good approximations, analytical approximations for their value. And thank you for your attention.
Thank you very much for your presentation. Again, Reini is clapping very nicely. Let me start the discussion with one question. You always use this kind of scaled intensity. What real intensities are we talking about? What would be a typical setting if you...
So you're asking about what the value of A0 means?
Yes. In relation to, there's a omega and there's a M and C, and there's the
yes, sorry, perhaps I moved a bit too fast. This is the definition of A0, and E0 will be the amplitude of our field. So you can invert this relation and you get that the intensity is A0 omega MC divided by the modulus of the charge. I'm not very good at converting from one unit to the other. I just multiply them when I...
And what would be the typical intensity? What would be the E0 numerical value? Order of magnitude.
I'll be honest, I don't know off the top of my head, but I can compute it for you if you would like.
No, not necessary. I can do the math, I guess.
Yes. Yeah, I'm more of letters than numbers.
Okay. So, yeah, Barry Walker has a question. Please take it away. Yeah.
So just a quick question.
Yes.
Are you using a focused arrangement with a Gaussian approximation here, or is this a complete numerical propagation of Maxwell's equation?
No. We use this solution.
It's completely numerical,
it's
right?
Numerical, right? So we have the solution, and then using this solution, we plug the numbers into the Faraday tensor to solve our equations of motion.
Okay, so that's what I want. So there's no approximation spatially here.
There is an approximation so far that the Laguerre-Gauss modes are in of themselves approximations, because if you try to solve the Maxwell equations for angular momentum, you would find the Bessel modes. But if you want to concentrate the energy, so you have something that's more realistic, like a laser to obtain, for a laser to obtain in the lab, you would probably use the Laguerre-Gauss modes.
Okay. All right. Thank you very much.
Okay. So I just took the numbers. I think it's some 10 to the 18 watts per square centimeter. Is that something you can agree with, or?
I think so. Yes.
Okay. Are there any other questions concerning this presentation? Not in the chat, I can see. So let's thank the speaker again.
Thank you.
And move on to the next and last presentation of this seminar today, or this session, which will be given by Alexander Silayev. And we come back to radiation generation. Alexander is from the Institute of Applied Physics in Nizhny Novgorod, of the Academy of Sciences, of the Russian Academy of Sciences, and he will tell us something about the multicolor and supercontinuum radiation generation in the terahertz regime. So please take it away, Alexander.
Thank you for the introduction. Do you hear me? Yeah.
We can hear you and we can see your presentation.
Thank you. First of all, I would like to start with the plan of my talk. It includes the introduction, the presentation of our earlier results on the generation of tunable single color pulses in terahertz and infrared ranges using gas ionization by two-color chopped laser pulses. Then I will go to our recent results on the generation of multicolor pulses and supercontinuum in these ranges, and then I will turn to the conclusion. In this talk, we are discussing the generation of pulses in mid-infrared and terahertz ranges, which corresponds to the wavelengths from the 3 microns to 300 microns. And in the frequency domain, it is from about 1 terahertz to 100 terahertz. So this is a rather wide range. And the generation of the pulses, short pulses with controllable phase in this range is very important for different applications. For example, the time domain spectroscopy of various media using these pulses, and for strong field science applications such as high order harmonic generation and so on. There are two main ways to generate such pulses, which include the nonlinear crystals and generation in gases. And in the second case, there are several advantages, which include the possibility to generate very broadband radiation and to tune it in the wide range, including the far infrared range. And also, the different advantage is the possibility to generate in gases, in ambient air, to use the ambient air as the working medium. To generate low frequency radiation in gases, one should have two color pulse. And the most simpler case is the case when the frequency ratio is close to 2. And in this case, for example, when there is the strong fundamental field at omega 1 frequency and the second harmonic field, which is slightly detuned from the doubled fundamental frequency, then the results of the four-wave mixing, the radiation at the detuning frequency is generated. And this frequency is small, so it belongs to terahertz or mid-infrared range. And the phase of the generated pulses is passively stable. It means that this phase do not depends on the phase of the fundamental field, which is the advantage of this scheme. If we increase the intensity of the radiation, the main contribution to the low frequency current density comes from the response of free electrons that are born due to the tunneling ionization. And this the current density of free electrons can be accurately described by this equation, which includes the free electron density, which grows due to the tunneling ionization. And as was shown in our papers and the papers of the other authors, the process of the generation of the radiation on the detuning frequency when using such two-color pulses with strong fundamental field and weak second harmonic field, which contains the small frequency detuning. This process can be characterized as a multi-wave mixing with the number of mixed waves, which is of the order of 10, and which is determined by the sharpness of the dependence of the ionization rate on the electric field. In this process, the one photon of the second harmonic field mixes with a very large number of photons of the fundamental field. And as a result, the radiation at the detuning frequency is generated. The efficiency of this process grows very fast with increasing the intensity of the fundamental field, which corresponds to rather high efficiency. And also the phase of this radiation is passively stable. Another property is the duration of the generated pulses. This duration is much smaller than the duration of the ionizing laser pulses because it is determined by the so-called ionization duration, which is the characteristic time scale of the averaged plasma density increasing. However, the important problem is the creation of the frequency detuning in such two-color pulses, because if one uses the frequency double crystal, which is inserted after the focusing system, the generated radiation at second harmonic is exactly the double frequency. And there is no frequency detuning. And in this case, we have the radiation in the terahertz range, which is determined by the plasma cell frequency. However, in order to introduce the detuning, one should use some advanced schemes. For example, it was proposed to use the frequency selective elements, such as dichroic mirror, to create the frequency detuning in the two-color pulse, and also the crystal rotation. In the last one scheme, the radiation can possibly be tuned. However, the range of tuning is determined by the bandwidth of the laser pulse, fundamental laser pulse, and it in order to make the large bandwidth, one should use a very short pulse, and there are some difficulties to obtain the bell-shaped radiation in the mid-infrared range and to tune its frequency. So there is a key problem which consists in the creation of methods to control the frequency detuning in the two-color pulses. One can consider the generation of such two-color pulses by using optical parametric amplifier, which generates the field near the half frequency. In this case, the tunability is rather high. So in this case, also the generation of on the detuning frequency can be obtained due to the four-wave mixing or the high-order nonlinear ionization-induced wave mixing. But in this was demonstrated experimentally in this paper, but the phase of the radiation is not passively stable. So one can stabilize it, but one should use the active stabilization of the fundamental field phase. In our paper published in the Optics Letters some years ago, we proposed a new method to generate the two-color pulses with frequency detuning, which is based on the using of the fundamental field, which is stretched and which has the frequency which grows in time. So it has a linear chop. And also the additional field, which is the second harmonic, which is also chopped, and also it contains some time delay with respect to the fundamental field. In this case, if we calculate the detuning frequency, which is the difference from the of the higher frequency and doubled lower frequency, we obtain the constant value, constant in time value, which depends on the time delay and chop value. So varying the time delay or by varying the chop value, one can control this detuning frequency, and so one can obtain the continuously tunable radiation in terahertz or mid-infrared ranges. And in order to test this method, in our paper, we solved numerically the time-dependent Schrödinger equation for the hydrogen atom in the two-color fields. And we have shown that in the case when we consider the parameters of the central wavelength 800 nanometers, the Fourier transform limited duration of the fundamental field from 5 to 10 femtoseconds, and the stretched pulse duration 300 femtoseconds. These parameters correspond to the current experimental possibilities. And we consider the two-color pulse with linear chop of the components, and we vary the time delay between these pulses. And we have provided the calculations for different intensities. Here is the result for sufficiently small intensity where there is no ionization. In this case, here is the power spectra of the generated radiation for different time delays, which are numbered by 1, 2, 3, and so on. And we can see that for each time delay, there is the bell-shaped peak, and the position of this peak, the frequency of this peak, exactly coincides with the frequency detuning from this formula, which confirms our suggestions. Then also we see that when detuning, when the delay is very small, when the second harmonic comes a long time before the fundamental field, there is no radiation. Also, it is in the case of the very high positive time delays. When the envelopes overlap, there is the radiation, but near the zero frequency, the signal is small, so there is no generation in the terahertz range. This is well explained by the response of the bound electrons, so due to the cubic response of bound electrons, because in this case, the time derivative of the current density is proportional to the squared generation frequency. So this explains why at small detunings, the amplitudes vanishes. And also, we can see that in this case of low intensities, there is no dependence on the sign of the chop, and there is no dependence on the sign of the time delay. But if we increase the intensity, we first see the amplitudes, high amplitudes in the low frequencies. Also, the efficiencies grows very fast with increasing the efficiency, with increasing the intensity. And third, there is the dependence on the sign of the chop and dependence of the sign of the time delay. These all features are well explained by the response of free electrons, because there is the response in the low frequency limit. Also, the radiation is asymmetric with respect to the sign of the detuning, which is proportional to the product of chop and time delay. In this slide, you can see the dependencies of the waveforms of the generated low frequency radiation when we change the intensity. If we increase the intensity, the duration of the radiation is decreased, which confirms the passing from the cubic nonlinearity to the high-order nonlinearity of free electrons. And I would like to also to discuss the maximal tuning range in this scheme. The tuning range is determined by the Fourier transform limited duration of the laser pulse. The smaller is the Fourier transform limited duration, the higher is the possible tuning range. And for example, when we have the 5 femtosecond Fourier transform limited duration, we have the tuning range about 150 terahertz, which is in the near infrared range. So this the tuning range covers both the terahertz and mid infrared and enters the near infrared. The lower limit of the tuning is determined by the stretched pulse duration, and by using the high stretching of the laser pulse, one can obtain very narrow peaks of the generated radiation, and so one can obtain the frequency tunability in the range of several terahertz. In our recent paper, we proposed the method to generate multicolor pulses in terahertz or mid-infrared ranges. And the idea is simple. We propose to use not one additional field at the second harmonic, but several pulses at second harmonic which have linear chop and which have different time delays. In this case, we have different detuning frequencies, and so we can obtain the generation on different frequencies. And we test this idea by solving the classical equations for the current density. In the case when the laser pulse consists of the fundamental field and m additional components on the second harmonic with linear chop. We first solve this problem analytically by using the perturbation theory, and we first we find that there are several components on the in the low frequency current density, which corresponds to the frequency detunings of different second harmonic components, which confirms our idea. And these components can be separately changed by changing the time delay of the second harmonic component. And also in the third order of perturbation theory, we obtain that there is the low frequency current density components in different triple combination frequencies. Combination frequencies. And these triple combination frequencies can have rather high intensities, which is confirmed by our numerical calculations. And here you can see the spectrum for the case when there are two additional second harmonic components in addition to the strong fundamental field. And there is the response in the main detuning frequencies and at the triple combination frequencies. If we increase the intensity of the additional field, we can obtain the supercontinuum radiation, which covers the frequency from 0 to 50 terahertz. And such generation is very important for different applications also. Here is my conclusions about the proposed method, about the possibilities to generate the multicolor pulses using the Gaussianization by chopped fundamental field and several time-delayed second harmonic components, about the possibilities of the generation of the supercontinuum. And here is the list of publications on this work. And also, I would like to pay attention to the one more paper that was recently accepted in the physical array, which is devoted to the method to absorb the wave function in the solving the Schrödinger equation, which can be useful for those who solve this problem numerically. Thank you for your attention.
Thank you very much for your nice presentation. Again, let me start with the discussion. I missed that part. What limits the range of the tuning frequencies? I mean, the small frequencies are probably related to the duration of the generating laser pulse, but the maximum detuning frequencies that you had here, this cutoff, what is the limit, or where does this limit come from?
This limit comes from the bandwidth of the ionizing laser pulse. So this bandwidth is determined by the Fourier transform limited duration of this pulse. So okay. The smaller is the Fourier transform limited duration, the higher is the bandwidth of the ionizing pulse. And the maximum possible tunability range is determined by this parameter. So if we decrease this parameter, the bandwidth of the generation pulse is increased, and so the tunability range is also increased.
Okay, thank you. Yes, there's another question by Barry Walker again, please.
So very nice talk, thank you. It went very fast, but I want to ask a question about your ionization rates, because you're using ADK as the fundamental source for your tunneling ionization, correct?
We use the formula that was presented by Tong and Lin.
Okay. So what sort of rates are we talking about here? Are they on the order of 10 to the 11, 10 to the 12, 10 to the 13? How close to saturation are we for this process?
This phenomenon of generation of tunable radiation can be realized for different intensities. For example, it can be realized also in the intensity range when there is no ionization, where is the response of bound electrons. But if we increase the intensity, the efficiency grows due to the fact that the response of free electrons is much more effective than the response of the bound electrons.
Right. But I guess what I'm asking is, obviously the atomic process saturates at somewhere around 10 to the 12 or 10 to the 11, depending upon your pulse duration. So yes, I'm asking what your rates are and how close you are to this saturation process.
In the present results, I use the intensity which is smaller than the saturation. But in our optics lattice paper, we also considered the case when the intensities are higher than the saturation. And there are some new features in this case. For example, in this case, the dependencies on the time delay becomes very asymmetrical with respect to the time delay. For example, the using of negative time delays becomes much more effective than the using of the positive time delays, because the ionization process goes on the front of the laser pulse.
Okay, I think I understand and I appreciate it, because the depletion effects in terms of the number of available atoms, right, when you operate at very high ionization rates, you have to include these depletion effects. And it looks like you've done that for these various situations, right? You deal with that.
Our numerical calculations based on the time-dependent Schrödinger includes this effect, and also our analytical theory also includes these effects because in our analytical formulas that we obtain, we have the factor. This factor is the time derivative of the averaged density of free electrons. and this factor saturates. So if you increase the intensity, this factor, the amplitude of this factor saturates, and the time interval of the ionization shifts to the earlier times, to the front of the laser pulse, and so this is also also seen in our formulas.
Great. Thank you very much.
Okay, thank you. And I do not see any further questions, neither actively nor in the meeting chat. So with this, let's thank the speaker again and all other speakers of this session of Seminar 2. With this, we conclude the Seminar 2 for today, and we will meet tomorrow again at 12 UTC, which is 2 p.m. at my time, and I hope you can calculate your times for the next session of our seminar. So thank you very much again, and hope to see you again tomorrow. Goodbye.
Goodbye.
Thank you. Goodbye.
Goodbye.
Bye.
Oleg, can Christoph and I stay in the session, because we just want to chat 5 minutes? I guess the session stays here until
I guess it will stay active till 7:30.
Yeah, okay.
Okay.
Gut, der Alexei Balakin ist noch da, aber das ist uns wurscht.
Der war vorher auch nicht da, glaube ich. Warte ich. Dann, ja, okay, passt. Ja, gut. Es war nie so viel los, dass man nicht alle Leute auf den Screen bekommen hätte. Also ich habe wenn man mit 2 Bildschirmen arbeitet, ist das überhaupt kein Problem.
Genau, außerdem ist ja so, wenn die Hand heben, dann rutschen sie ganz nach oben.
Das habe ich irgendwann bei den vielleicht auf meiner Seite, aber bei den großen Vorträgen, beim Plenary habe ich das nicht gesehen. Da war irgendjemand, der die Hand gehoben hat, und der war auf Seite 2 oder 3, und das hat zwar der Chair gesehen, aber ich habe es nicht gesehen. Den habe ich suchen müssen. Aber
okay, also bei mir springt es immer rauf.
Okay.
Wenn wer die Hand hebt, dann...
Ja, also ich habe jetzt alle im Blick gehabt, weil eben der Bildschirm groß genug ist dafür. Aber die in der Nachmittagssession sind ohne dies weniger Leute, also das war einfacher jetzt.
Ja, also ich glaube, wir brauchen jetzt auch gar nicht irgendwelche Instruktionen
Na, es hat
für die
alles
Chairs rausgeben, weil, also ich bin sowieso in die Sessions, und falls irgendein Chair sich nicht auskennt, dann funke ich halt rein. Also.
Ja, und heute hat er mich zum Co-Host gemacht, weil ich immer als Erster da war, aber dann wird er dich zum Co-Host machen, vermutlich, und dann kannst du noch immer bei der Session irgendwas anmachen.
Genau, und die ist ohne das freigeschalten für alle. Das ist ja, glaube ich.
Ja, es ist gut gelöst, ja.
Das ist gut gelöst, genau.
Ja,
ja, jetzt haben wir das einzige Problem noch, dass der Muckermel nicht wegen Session Chair geantwortet hat.
Der wäre am Freitag, oder wie?
Der ist am Freitag, ja. Ich meine, im schlimmsten Fall mache ich das auch nochmal. Ich schreibe ihn nochmal an heute, aber das gefällt mir jetzt nicht. Das ist mehr Aufwand, jetzt da blöd durch die Gegend fragen, als dass ich es halt selber mache. Weißt du, was ich meine?
Ja, du hast ja nachher den Chair von der Plenary, gell?
Genau. Ja, aber das ist trotzdem, also.
Ja, nein, ich kann am Freitag sowieso nicht, da bin ich nicht da. Oder
genau.
Nicht. Aber, ja. Hoffentlich meldet er sich noch. Hat er irgendwo einen Vortrag? Nein, gell?
Ja, am Freitag in der Plenary Session, wo ich bin.
Ach so, ja, dann ist er ja auf jeden Fall da. Also dann wird es kein Problem geben.
Ja.
Hat er nicht geschrieben, hat er nicht geschrieben, dass er 3.4. Mehr oder weniger nicht verfügbar ist, weil er irgendwie übersiedelt oder was? Oder irgendeine Übersiedlungsaktion ist? War das nicht das?
Das weiß ich nicht mehr genau. Auf jeden Fall hat mir der Oleg die E-Mail-Adresse von der Sekretärin gegeben und hat gesagt, die ist normalerweise schneller. Und ja, vielleicht, genau, ich schreibe ihm morgen Abend, schreibe ihm nochmal und dann sehen wir es schon.
Ja.
Genau. Ja,
Ich
ansonsten.
weiß, das war irgendjemand hat ja geschrieben, dass er 3.4. nicht wirklich verfügbar ist, weil er.
Ja, war das nicht das Sign-Through?
Ja, ist möglich.
Ja.
Ja.
Wurscht. Egal.
Ja.
Ich schreibe ihm morgen Abend und wenn er einfach nicht antwortet, dann mache ich es. Kein Problem.
Okay. Na gut, dann erfolgreicher erster Tag. Hat ganz gut funktioniert, glaube ich.
Ja, Vorträge waren auch gut.
Ja. Vor allem der letzte hat mir jetzt sehr gut gefallen. Der war ein bisschen zu schnell, aber viel Material.
Ja. Na okay, dann sehen wir uns vermutlich wieder
Morgen.
am Bildschirm.
Ja, morgen und übermorgen bin ich noch da und am Donnerstag bin ich dahin.
Sehr gut.
Okay,
Passt.
gut.
Dann
Servus.
bitte.
Servus.